Okay, welcome to the building of the ngEHT instrument and outreach. Our first talk will be given by Helge Rothman from the MBIFR. Please, Helge, you can start with your presentation. Thank you very much.
Can you see the presentation?
Yes.
Okay, 1 second. Okay, I want to report to you on a new hardware project that is carried out at MPI in collaboration with enough, and the aim of it is to build next generation Vlbi backend named the DVB-C4. Just to give you an overview of the context, the DVB-C4, as the number at the end suggests, is a next member in the family of DVB-C backends. And there is a fairly long-lasting collaboration between enough and MPI. It's started in 2009, and it resulted in 2 families of DVB-C backends. That is the DVB-C2 that was quite successfully used. I think in the field of Vlbi, there were more than 40 units out in the field. And more recently, the successor, the DVB-C3, which is the current workhorse, I would like to say. And at the moment, there are already more than 25 units out in the field and 16 are in production, so it is comparable to the DVB-C2. The maybe remarkable thing or different thing about the DVB-C philosophy is that it is a very versatile instrument. So unlike, for example, the R2 DVE that we use for EHT, is a very dedicated instrument to do exactly what the EHT wants to do. The philosophy in the DVB-C backend is to be versatile and to allow to accommodate for Vlbi observations in various scenarios. So consequently, it's used, the DVB-C2 and 3 is used in various networks, prominently in the European Vlbi network, but also heavily used in the GMVA, and also in the EHT. Actually, 2 telescopes are equipped with DVB-C3 backends. It's not only used in astronomy, it's also used in the geodetic field. So some IVS and BGOS stations make use of that. And the same philosophy also holds true for the DVB-C4. It follows the same versatile approach. So we expect it to be also applicable, usable in various Vlbi fields or networks. So just a bit about the technical specs. So at the heart of the DVB-C4 sits a fairly advanced component that is a sampler chip, which operates at 56 gigasamples per second at 8-bit. The effective bits are about 6.5. But concerning, in terms of bandwidth, that's still a fairly impressive piece of hardware there. The DVB-C4 is a modular design like the 2 and 3, so you can add a number of boards depending on the number of IFs that you want to process. But in principle, the maximum build that you can do consists of, you could process 8 times 28 gigahertz of bandwidth in analog or digital form. There is an additional possibility to add another 8 times 4 gigahertz. So if you add that up, you get to a full aggregate bandwidth of 256 gigahertz, which a single DVB-C4 system will be able to process. Consequently, the output data rate is high. So in the case of Vlbi 2-bit sampling, we will output data at 1 terabits per second. But also it will be possible to output 4-bit sampled or 8-bit sampled data. The DVB-C4 will, just like the other models, offer various modes of operations. So there will be full band mode, there will be a filtered subbands, and There's also a tunable mode where you can place your DDC subbands at arbitrary positions of your input bands. The DVB-C4 will implement some advanced features. I'm not aware of any Vlbi backends that implement any of these. Just to highlight three. Will be that it includes an artificial intelligence controller that can be used for various tasks. And the obvious thing to do is to try to do RFI mitigation in near real time. That is a very relevant problem. If you go to these large bandwidths of 28 gigahertz IFs, you would very likely be confronted with RFI in your band. And since also the bits of these samplers, even though we have 8-bit, that's not quite sufficient to fully cope with that. So it's a very important task to be able to reliably remove at least the strongest sources of RFI from your bands. There are other possible applications for this, like transient searches or detection, possibly other things. So that will be an interesting field to explore in the future. The DVB-C4, I mentioned that it will have fairly large amount of memory buffering capability, and that can be used also to do other things, like you could duplicate output streams. So one scenario is that you record one stream onto the recorder, but you could also duplicate a stream and stream it into the network, and where you could also do decimation in terms of frequency and time, and that offers interesting possibilities. For example, one could think about real-time fringe check capability during a session, which would naturally or greatly has the potential to greatly increase reliability of Vlbi observations, where typically we're pretty blind in terms of what we're actually doing at the moment at a station. I will skip the architecture. That's not very interesting. And this is my last slide now. So the DVB-C4 project, I wanted to report a little bit on the state of it. So we have submitted a funding proposal to the Max Planck Society in August. And actually, it has been reviewed already at the end of October, but we haven't been notified yet. So that's expected to happen actually in a week or two or so. The total project volume that we estimated is about 2.2 million euro. And we expect work to be carried out over the next 4 years. So if everything goes well and we receive funding, we are in good shape to start the project right away. We have all the necessary components and so on in-house, so that we can resume work more or less immediately. And so I'm crossing my fingers that this will work out. And if everything goes well, that would be an interesting option for the ngEHT also, as the DVB-C4 in principle would be capable to in terms of bandwidth and so on, to address the requirements there. Okay, thank you very much. That was it.
Thank you very much, Helge. We have 2 minutes for questions. I see Eduardo raised his hand. Please go ahead, Eduardo.
No, Jonathan, you know, I was just clapping.
Oh, Eduardo, you didn't have a question. Okay, okay, Helge, great talk, and it's just an amazing system, I have to say. It's incredible. I'm not going to ask my usual question, which is when can I get one and for how much? So I'm not asking that question. I actually would like you maybe to comment on recording. I mean, you mentioned it's got a burst mode so that you can accumulate very, very, it's multiple terabits per second out. That's very hard to record. So you've got all this buffer memory and you can accumulate it on board and then spool it out to a slower recorder like a Mark 6 or maybe one of these new 128 gigabit per second recorders we have in mind with SSD. But do you have any other tricks? I mean, are they countenancing approaching terabit per second recording in a sustained way? Is your team, I should say, looking at that at all? Because recording is really part of this whole, or data transport in general is like the hard problem that comes when you build very, very fast backend.
So we are not really working on any recording concepts there. We really fully rely there on other groups and people to take care of that problem. But I agree that is a fundamental bottleneck which we will be facing. I should say, however, that this 1 terabit per second, of course, this is this is like the maximum scenario where you would have 8 times 28 gigahertz of bandwidth. So I think that is not on the horizon realistically anywhere yet. So the realistic data rates will be lower, that we have to cope with will be considerably lower at the moment, at least. Okay,
great. That's fair enough. Thank you.
Remo Tilans raised his hand.
Yeah, so basically I echo Jonathan's actually question. That was exactly my question regarding the recorder options. I mean, everybody is jumping onto the bandwagon of developing digital backends, unfortunately, and at the expense of not looking at the recording. I would only ask to submit a plea to anyone involved with the ngEHT to start a dedicated project on recorder options, please. It's always tacked on to something, but I think we need to start focusing on this fairly rapidly now if we want to have any viable option also for the intermediate term, because the EHT, in the back of their minds, we want to double the bandwidth to some, for instance, to the smaller observatories, and I don't think we can field 8 Mark 6s.
But I thought, Remo, Jonathan is just doing this in the next years. That's what I understood.
Carl, you saw my proposal. It was, which I passed by the EHTC board. That proposal for dedicated recorder development was declined by the National Science Foundation. Unfortunately, I should perhaps have updated you.
Yeah, then send it in again.
What was that?
It was a good proposal. It was a good proposal. So.
I've done very well this year with proposal declinations. I'm really very much ahead of the game. It wasn't the only one.
We all are.
I can count 3 in 2021.
Keep on going, John.
I appreciate that. I very much appreciate the kind words. And it is sort of a response to Remo to say that I personally view recording as a very important subsystem development, commensurate with.
I'm sorry, I need to interrupt you. We need to move on for the next presentation. Please, we can continue your discussion either in the chat or in the dedicated Slack channel.
Yeah,
so,
Vincent, please add your comment in the chat.
Yeah. So let's move on to our next speaker, Mr. Volodymyr Kudryashov, which is going to present us the presentation with the title "Demonstrated Performance of Local Oscillator Broadband for the Event Horizon Imager." Please, Volodymyr, go ahead.
Thank you, Sally. Can you hear me? Can you see my screen?
Yes.
Very well. First of all, thanks a lot for this opportunity to give presentation here. So I will try to be on time in sense of duration of presentation. So the idea is to report results we got here in European Space Agency with breadboard we built to check a concept of making two local oscillators coherent enough to think about Vlbi in space. So the presentation consists of introduction, problem description, problem we can see with lack of coherence for sub-millimeter Vlbi from space, and then concept description, breadboard developed, and test results we obtained. So we think that killer science for a next generation space Vlbi requires imaging black holes with angular resolution of 5 micro-arc seconds, which is 1/10 of the size. But considering scattering broadening towards Sag, observation frequency should be above 486 gigahertz, so above half terahertz. And then atmospheric phase difference on Earth scale baselines and such a short wavelength also calls for space Vlbi. And then Manuel Martin-Neira from Space Agency came with idea to explore circular medium Earth orbits. And here on the bottom left of the slide, we can see comparison of UV coverage between ngEHT. And this concept was by Manuel. So UV coverage is potentially very densely populated. It's very symmetrical, which is good for beam. Also, UV coverage is bigger than we can get from the ground because we have more space. But if we go for even higher observation frequency as needed to avoid beam broadening, then we can get quite nice, I think, image reconstructions as demonstrated by Freek Roelofs from Radboud University. Now he moved to the United States. As we can see on the bottom right of the slide, image reconstruction at 690 gigahertz it's just beautiful. But one of problems is that such instrument has to be coherent. So oscillators on two separate satellites have to be quite in line together with each other. So here I have to acknowledge Leonid Gurvits. I think he is here present for support for references at the beginning of this study, because he suggested the way to compute coherence. So on left-hand side, we have a kind of collection of oscillators we thought about just to make comparison, and also a kind of requirement. So we can see that basically there is no clock for our demand. With best measures we go maximum to 10 seconds, or if we take the best active hydrogen measure for ground, which is I measure 2000 used for ngEHT, we can go up to 40 seconds only, which is far cry from the longest unsmeared integration time. The latter is 450 seconds. So effectively, the coherence loss, if we integrate 450 seconds in one run at such a high frequency, coherence loss is about 12 dB. And in the front end, I cannot see any margin to recover that 12 dB, because we already thought about cryogenic receivers, biggest dish we can put in the variant of launcher, widest practical bandwidth, etc. So it really looked like a problem. And then Manuel Martin-Neira came with concept, which I tried to sketch here on the left-hand side. So we have two satellites, A and B, with two OCXOs on board, OCXO-A and OCXO-B. So OCXO-A gets output of OCXO-A gets splitted, and one of outputs of the splitter is sent to counter satellite, to satellite B. Same happens at satellite B. So the OCXO output is sent to satellite A, and then we just take sum of them. So the idea is that the sum will be same on boards of two satellites because the inter-satellite link length is same. The rate of change of this length, so the Doppler is same. So it was the idea. And then from point of view of making breadboard, we also thought about some design drivers. So we thought that to be thermally immune, we have to maximize frequency multiplication factor before optical frequency transfer and minimize the frequency multiplication factor after that. Also, we thought about realistic performance of building blocks that we can get on market. So we cannot transfer 100 gigahertz over optics in lab at this moment. So we had to be a little bit more practical and modest. But before doing design, we did also some simulations. So Manuel came with this equation for phase noise variance. And the good thing about this equation is that with increasing of integration time on each baseline, the phase noise drops down because integration time is in denominator, so it's in power of -2. And then the integral of phase noise from 0 to integration time, it has two multipliers. Multiplier 1 in round brackets, multiplier 2 in square brackets. So multiplier 1 goes down with increasing of integration time. And structure of multiplier 2 is 4 times gamma, no matter for now what is gamma function. So 4 times gamma minus gamma, 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 gamma. So the equation is phase noise cancelling by itself. So ultimately, if we make microwave system quite good, then maybe we can have good results. This was the feeling. So we started building it, and we thought about following design inputs. So frequency multiplication factor before optics should be much bigger than after optics, as I mentioned. Then we had a dream to do some demonstration on site ERAM. So we thought that maybe we can drive tripler on board ERAM with our output. So we thought about making output at 100 gigahertz. Then we thought about balance mixer, which can do for us the frequency adding, but turned out that if we want balance mixer with equal frequency at both inputs, then its market runs quite short. And also optics we can use can transfer nominally up to 18 gigahertz and can receive nominally up to 50 gigahertz. In practice, it works at higher frequencies, but we discovered it later.
1 minute.
Also, say it again, please.
1 minute, please.
Okay, I will go faster. So this is picture of the setup with 2 breadboards, VNA used to make measurements, optoelectronics, and 5 kilometers of optical fiber. This is another picture, names of blocks in one of breadboards, and this is obtained performance. So measured performance is 10 to minus 14 over tau within time up to 1000 seconds. It is about 10 times better than required, even including degradation due to longer fiber than 5 kilometers. And then we tried also with temperature variation, plus minus 3 degrees, which means quite the worst case. And also the result, Allen deviation is immune to that. So overall, breadboard satisfies requirement with order of magnitude margin at least. The result follows temperature difference, but the Allen deviation obtained is still good. And the phase difference between derived local oscillators at 100 gigahertz is about 0.5 degree, 1 sigma during 3 hours. This is plot on the right-hand side. That's it. Questions? Any questions?
It seems that at the moment we don't have any questions. If someone have one, we can post it in the Slack channel. So thank you very much, and let's move on with our next speaker, which is So Masui. Please, So, go ahead.
Okay. Can you see my slide?
Yes.
Thank you. Thank you for your introduction. I'm Shomasri and a PhD student of Osaka Prefecture University and National Astronomical Observatory of Japan. Today, I will talk about development of dual band polarization and dual polarization and dual band receivers that allows simultaneous observation at 213 and 345 GHz frequencies. They are collaborators of this work. This is the content in this talk. Initially, I will introduce the development of 230 and 345 GHz simultaneous observation receiver system with a single polarization, and show observation results with the receiver installed on 1.85 meter telescope. This development is described in detail. This development is described in detail, Masa et al. 2021 and Yamasaki et al. 2021, published in Publication of Astronomical Society of Japan. If you are interested, please check out these papers. Next, I will report on ongoing development of wideband polarizer and osmo transducer for efficient observation. Finally, I conclude our development. First, let me introduce the 1.85 meter telescope. The 1.85 meter telescope of Osaka Prefecture University has been operated at the Nogoyama Radio Observatory in Nagano Prefecture, Japan, to observe molecular clouds in nearby star-forming regions and along the galactic plane in the molecular lines of 12CO, 30CO, and C80O J221. The detailed specification of the telescope are described in Onis et al. 2013. So far, we have been simultaneously observing these lines using a receiver composed of circular polarizer and diplexers. Okay. Recently, we have newly installed a wideband receiver for simultaneous observations of CO isotopology lines with transition of J221, 322, and other molecular lines. Here is the wideband simultaneous observation system. The waveguide multiplexer consists of wideband diplex alpha and two diplexers beta and gamma. The wideband diplex alpha provides frequency separation between 210 to 275 GHz and 275 to 375 GHz. The two output ports are connected to each diplexer beta and gamma, respectively, and eventually separated into 4 frequency bands. Furthermore, by using an SS mixer with a broadband I output described in Kojima et al. 2020, we took on the challenge of receiving 3 CO lines in the 345 GHz band with a single mixer. The 3 diplexers that make up the multiplexer consist of branch line couplers and high-pass filters. In addition, the local oscillator couplers are included in this configuration. A schematic with a slightly modified configuration is shown on the right. Due to the time constraint, I will skip the detailed explanation. As the wideband receiver was assembled and integrated on the telescope, we have succeeded in observing the 6 CO lines J221 and 322 toward Orion Care simultaneously. Here is the observation results. The x-axis is the velocity of local standard of rest, and the y-axis is the antenna temperature. As you can see, the 6 CO lines are received. Okay. Now we are developing a new waveguide component to extend the capability of the current wideband receiver system to a dual polarization observation. 2 types of polarization observation can be performed by using a 90-degree phase shifter and OMT for circular polarization, or OMT only for linear polarization. This polarizer will be inserted in front of the current waveguide multiplexer system described in this presentation. We also would like to contribute to both ALMA and Vlbi telescope projects we are conducting waveguide technology development for both circular and linear polarization observations. And therefore, we are developing two important components, the phase shifter and the OMT. Okay, first, let's talk about the design of the phase shifter. To achieve a wide bandwidth, the phase shifter was designed on the basis of the concept that combines multiple phase shifters so as to reduce the frequency dependence of the phase difference. Here is a designed phase shifter. In this design, we aim to set the amount of phase difference to 19 plus minus 6 degrees so that the cross polarization would be about 25 decibel. Here is a fabricated phase shifter. The simulation and measurement results are described below. The left side shows the magnitude of the S parameter. The horizon axis shows the frequency. The left and right vertical axis shows S11 and S21 in decibel, respectively. As you can see, the measured S parameter is close to the simulation. The graph on the right shows the comparison of phase difference between measurement and simulation. The horizon and vertical axis are the frequency and phase difference, respectively. For the amount of phase differences, we found that there was a discrepancy between the simulation and the measurement. To investigate the root cause of this discrepancy, we checked how large fabrication error exists in the phase shifter by using a QNS microscope as dimensional measuring instrument. As a result of the measurement, it found that the overall fabrication was done with good accuracy. But as shown in the figure on the right, 3 to 5 micron burrs were standing at the corrugation area. As shown in the lower left, simulation using a model with burrs shows that the reflection loss is less affected, but the phase difference is greatly affected. The graph on the right shows how the amount of phase difference varies with the height of the burr. We concluded that the difference between the simulated and measured results could be due to the presence of burrs. So we decided to do some additional processing. Then after the additional processing, we could achieve this result. Comparing the simulated and measured results, it is a very good agreement. And next, the designed OMT is based on double-reached waveguide Beaufort junction. To avoid unnecessary waveguide lengths, we applied miniature flanges. The simulation and measurement results are shown below. In the simulation, the reflection loss was about 21 decibel, while the measurement results was about 17 decibel. We assumed that one of the reasons for this is the effect of the transitions that is connected to measurement system. And we are currently trying to remove this effect. However, the overall performance of both the waveguide components is pretty good. We believe that, thank you. We believe that developed components shown here can be directly used for some astronomical applications such as ngEHT project. In summary, we have developed a waveguide-based wideband Mark spectra covering a frequency range of 210 to 375 GHz for the simultaneous observations of 6 lines of J221 and C2. Furthermore, we are developing both a polarizer and OMT to observe these lines with dual polarization. Blackburn et al. 2019 lists simultaneous observations of both polarization at 230 and 345 GHz as a development of instrument to achieve the science goal of ngEHT. I think our development is in line with the development suggested in ngEHT project, and one of the options to achieve simultaneous observation of both optimization at 230 and 345 GHz. That's all. Thank you for your attention.
Thank you very much. Any questions for our speaker? Okay, it seems that there is no question now. So let's move on to our next talk by Jens Kaufman. Jeff, please go ahead.
Thank you very much.
Hi, one moment. You can see my slide?
Yes.
Okay. Yeah, thanks for giving me the opportunity to talk in this forum. And I want to talk a bit about ngEHT and the overall astronomy and radio astronomy community. And some of this, for full disclosure, is based on a kind of melancholic retrospective of the URO program. So I was at Karma, was spending a lot of time at Karma about 10 years ago. And for those who don't know, the URO was the University Radio Observatories program, which was run by the NSF from 1991 to roughly 2012, and was dispersing funding at a rough rate of, say, $9 million per year. And some of this has been replaced by the MSIP, the NSF, but at a vastly different spending rate, and not necessarily for the same type of work. And that has impacts on the radio astronomy community, as I'm going to explain. In case you are interested in some of the details, I wrote an Astro 2020 APC white paper on some of this. And you might find some of the details there. So let me first talk about URO program and what it meant and what the issues with it going away. So let's look at some of the successes of the URO program. So it trained more than 160 PhD students and postdocs, for example, with year 2010. It had a huge impact on radio astronomy facilities. I'm not going to go through the details here, but it goes up to NRO directors who were trained at some of the facilities financed by the URO. And of course, the URO program also delivered important components for ALMA. So it was really essential for building the facilities which we all like and love nowadays. And of course, a specific example here in the context of EHT, KARMA, SMT, and CSO were critical in laying the astrophysical groundwork for the current EHT. So without the URO realizing what we are discussing about today, it would have been very difficult. I'm not going to go through the exact problems here that I'm laying out with that program essentially disappearing to a large extent, but to make it brief, it's hard to get quick hands-on access time for observers as well as technologists on facilities in the radio domain at the moment. There's a good reason why we are nowadays dominated by professionally run facilities like GBT, JVLA, and ALMA. They are really great as research instruments, but not necessarily so good as education and test facilities. And that creates certain problems. So some of the consequences, I think there's a bit of an emergence of black box thinking in the sense that astronomers, observers get delivered perfect data sets with perfect calibration. And therefore, they are not really understanding that some of the things they see are actually artifacts. It can be difficult to commission and operate observatories if you don't have well-trained staff who spend postdoc and student time at not so greatly run facilities. There is a problem in developing technology for future instruments if you lack the test beds. You have limited opportunities for non-standard observations like ngEHT if you only have the big national scale facilities. And there is a general problem when the community shrinks. Well, it means that there are fewer people interested in radio astronomy, for example. And that can be related potentially to some of, for example, the North American ulnar oversubscription factor is relatively low compared to other communities, maybe as a result of this. Anyway, there are various problems and they can be demonstrated with specific examples. So how could you address the problems with URO going away? It is possible. One possibility would be to have university employed staff involved at major observatories or array substations. So if you think about the ngEHT or the ngVLA, some of those stations could potentially be run by universities. And I don't mean the current stations, but future ones. On those facilities, it would be good to actually allocate time for observatories, for universities to do their own experiments on their own responsibility. And obviously it would be great if those smaller facilities and smaller universities could be related to NSF funding streams. Just to give you some examples out of the ngEHT context, at Haystack, for example, we are at the moment receiving funding for a receiver upgrade. So this is a good example how this could actually work in practice, or it's already working in practice to some extent. And as I suggested, it might be interesting, for example, to operate some of the new ngEHT dishes by universities and give them independent test time and operations time. That would have certain design requirements. So you have to be open to funded collaborators in building out the ngEHT if you want to have the ngEHT contribute to this. And I personally would hope that the ngEHT dishes are designed as multi-purpose dishes with larger receiver cabins and larger apertures, or both on the high end, so that you have more flexibility, both in terms of instrumentation as well as the scientific applications, including single dish work potentially. Let me relate this to the overall landscape. I think this meeting shows that there's tremendous interest in the community in the ngEHT, but it wouldn't be the first instrument that's really exciting that doesn't get built. For example, for the CCAT project that also received a lot of endorsements, it didn't get built, and maybe because some people in the community or people outside of the radio community thought this is a one-trick horse, so not really exciting for the overall community. And the ngEHT needs to avoid this, and I think this meeting here is a good way to avoid this, but it needs to be baked into the project concept that the overall community needs to be involved. For example, with having an exciting and broad science case, because you are not, black hole movies are great, but you're competing with exoplanets, and that might be of interest to other people. So if you can offer more things to more people, that would be great. High duty cycle, I think it's important to have a telescope that spends more than 50% of its time doing useful things. Unified community, whatever comes out of these discussions, it needs to be really supported by the overall community of researchers involved in these projects. Speaking with one voice, because any discord will be sensed right away by the community. This is a several $100 million project, so you're competing with very big communities, and there needs to be unified voice. And Obviously, if you can show that you contribute to education and technology development, and also have a financial benefit to many other institutions, that would be great because it increases the pool of people who really like this project. Thank you.
Thank you very much. Your talk, any questions? Okay, let's move on then to our last talk for today. Gordon Mcleod, please, you can start. Thank you.
Thank you. Let me just see if I can find my presentation. Hold on. Yes. That's it. Right. Start. Oh, I gotta share screen. Sorry. Let me first share screen. Yes. So I hope you can see this. Can you hear me and see me?
Yes, yes, we can hear
Great,
you and see you.
I'm presenting on behalf of a group of members of the university, the Open University of Tanzania, and we've been working on this project for some time to develop astronomy on Kilimanjaro. It started about 10 years ago, and it really started with a simple question that I asked the delegation of government officials visiting the Department of Science and Technology in South Africa, where I was working on the SKA at the time. And I asked them simply, they wanted to get involved. And I said, well, why don't you just think of doing astronomy on top of Kilimanjaro? And they said, can we? And this is where it all began. Myself and Norley have been at this for some time, and Celia joined us, as did ngEHT, and now the Vice Chancellor really champions the cause. And they've given us a lot of support over the last 10 years. And I can say now with confidence, we've actually got to the stage where we can get onto the mountain and do site testing. So the Minister of Tourism, and I'll explain that in a moment, but the Minister of Tourism sees this as a rather exciting project. And likewise, so does the Ministry of Science and Technology, of course, but he's been driving it from his side because Kilimanjaro is in the parks, the National Parks Program, and it's above a protected rainforest. So, you know, there's a lot of issues that one has to resolve with that. But anyways, the project has been running along, takes time. And we are now sitting at beginning site testing or site qualification above 4,500 meters. Probably on the saddle, you can see on the lower right-hand side, I've got a yellow marker on Google Earth, which is a fantastic tool for doing this kind of thing, because you can look at elevation and all sorts of interesting stuff. Anyways, we wanted to go to Mwenzi Peak, and when I climbed the mountain in 2012, I wasn't allowed to because I don't have my ropes certification. So I wasn't able to go to the 5,100 meter mark. I was forced to go up to Uhura Peak at 5,895, which is exciting, but we can't do astronomy up there and it would destroy their tourism. So that was a no-no. Anyways, so most of the sites we will look for will be on the saddle between the two peaks towards Mwenzi Peak itself, most likely. We'll do testing at about 4,700 meters, because that's the most secure place on the mountain to run equipment. And that's where the project stands right now. We literally are in testing phase. So we hope that the picture you see of the night sky is what we see every day of the year. But of course, that's not the case. We know there's the rainy season everybody has to deal with in the tropics. So this is our team. We've been moving forward and we're looking forward to site testing. So let me move on and say what we've been doing in Tanzania itself. In this time, we've put together what is our consortium of universities and whatnot, led by the two ministries. And in particular, the Ministry of Tourism, as I pointed out, they are responsible for the national parks of Tanzania. So TANAPA is the short name for them. And we have to partner with them because, of course, we have to satisfy all of the issues regarding environmental impact, the aesthetic aspects on the mountain, et cetera. And that's what we do. But we also have a consortium of universities that have also joined us. So we have a substantial critical mass now that we think we can use, not just to drive the project on the mountain, but rather to introduce astronomy and science into the curriculum astronomy into the curriculum from K to 12 and the university level. And with that, we also wish to train others that will carry forth this process. So, so let me just carry on, and my third slide, this is not very long really. The real driver for this is Astro Tourism, and that may sound odd because Astro Tourism doesn't get people in airplanes to fly to Tanzania to look at telescopes. The reality is that every time, there's about 25,000 visitors to Kilimanjaro, and that generates about $50 million to the local economy. And overall tourism generates something like $2 to $5 billion annual to the Tanzanian economy. So this is really the poor cousin. And the reason for that is because it's what's what I'm looking for here. It's adventure tourism. Adventure tourism is a person like me. One of the members in this audience called me an adventurer one time, and I guess it sticks. But I mean, I've climbed mountains. So the point is that I was happy to go up this mountain because I enjoy being at altitude. Those people are willing to go anywhere and suffer a little bit. They don't care about the conditions of what they're sleeping in and whatnot. And they probably pay less, and there's fewer of them. So you don't generate the same amount of money as you would in the Serengeti on a game drive, right? So that's the idea. So the reason why tourism ministry like this is that we were proposing a rather grandiose plan. We actually originally proposed building a cable car to the saddle, which could increase the tourism in the area from 25,000 to 1 million visitors a year. And that would have been a substantial improvement in their economy, generating up the order of $1 billion to $2 billion. But it would have costed $1 to $2 billion in total investment. So of course, they've now gone with a much smaller plan, which is to build a cable car to the top of Shira Peak, which is the third peak at about 3,500 meters. It will generate a reasonable income for the country. And in the longer term, we will see what happens. But the people at the bottom are my bosses. These are the people I work for. Whether I do astronomy or not is irrelevant. Those people work their backsides off every day, and they're the people, you know, helping to generate that 50 million for the economy of Tanzania and for their families, most importantly. And they are my bosses. So what we want to do is we'd like to train them basic astronomy, and also, you know, giving fireside night viewing lessons, etc., so that they can do a value add to their clients when they're taking them up the mountain or going into the Serengeti and any of that stuff. So our target market for Astro Tourism will be that. Anyways, the long and short of this whole story is that astronomy isn't simply about the science. All of the talks I've heard so far have been about the prestige of the project, you know, how many PhDs you get, how many great papers you produce. The second is, of course, the human capital development, the PhDs, the students, the teaching. The third is the technologies that many of the authors have spoken about. But this is the fourth. And a lot of time astronomers don't think about the economic impact of their projects. If you build $1 billion project on top of a mountain somewhere, it's going to cost $100 million a year, plus minus, to operate. $60 million of that $100 million will go into the local economy because you have to employ management and staff in and around the mountainside to run the facility. This will be true for most places, 10 to 15%. And that's one aspect. The other aspect is what we're talking about here. And that is finding ways to maximize the economic potential. And you have to talk to everybody. You know, you don't just talk to the scientists, the educators, the engineers, you must talk to economists. You must talk to entrepreneurs. And this is what this project was born of. And as I said, these are my bosses, these people here. And they're the ones I'm trying to improve their lot and help and find ways to do it. Not least of which, we're going to provide a facility that will improve, you know, it'll give us medium range baselines between the West African site in Namibia on the Gamsberg, which I've also visited. So those are very good sites, but of course you need those mid-range baselines, obviously, so you get better UV coverage. We all know this. And this will be another example of that, but there is more to it than just the science. It'll be a small facility, I'm sure, to start, but for the Tanzanians, it means that we can have equipment in Tanzania for Tanzanian students to train on, and that's another group that you're going to excite and educate the next generation of scientists. And I can assure you, out of this group of people you see these pictures of, these people are exceptionally gifted. And one of them may have been the next great scientist that we find. And with that, I will stop and you're welcome to ask me questions. Thank you.
Thank you very much for the presentation. Questions, please.
Right, well. Okay, good.
Sepp Gelman is raising his hand. Please, Sepp.
Hi, everybody. Thanks, Gordon. Very nice talk. And for those of you who don't know, I've been talking with Gordon and with many of the people in Tanzania about this possibility. It's very, very exciting. I was really glad to hear you say, Gordon, that the human component in a situation like this is extremely important. And we had some very interesting discussions earlier on the cultural aspects that we'll have to pay very, very close attention to as well. It's not just the economic, which is vital, but it's also embracing the local culture as well, to make sure that we work hand in hand with everyone locally to forge a new facility that everyone is invested in. And of course, the Kilimanjaro site is quite good atmospherically. I mean, there is a raining season, but it may well be the best site in all of Africa to stage these kinds of observations from. So the fact that this is moving along is really wonderful. And thank you for your efforts in pushing it along, and to those in Tanzania.
My colleagues and I'm sure will thank you for that compliment. That it is we were given 3 issues. We were given 3 issues to resolve. Let me just say this quickly. The first was the environment. You cannot damage. It's a heritage rainforest site. So of course you have to find a way over the rainforest without damaging it. The second is the aesthetic beauty of the mountain. And the third is it has to be economically viable for the country. But the fourth, as Shep just pointed out, is cultural. And we added that in. So, you know, these are issues, and there's always a solution. I always tell people there's always a solution. It just costs more. So this is one of those projects. It's taken us a lot of time, but thanks, Shep, for your continued support.
Thank you. Nural has also raised his hand.
Nurali, you're muted.
Okay, hello everybody. I hope you can hear me. So I'm Jiwaji, Nurali Jiwaji. I'm one of the members of the Tanzanian team, and we have been pursuing this with Gordon for several years. And we are glad that we have reached this stage, but this connects with the previous presentation that this is really about taking these projects to universities. I mean, the involvement of universities and putting it into their programs, into the research, or different types of, we've talked even in terms of environment, social impact, environmental impact, cultural considerations, economic, all these can be done through universities. So I'm very pleased that we are at a stage where we can make an impact on university teaching and research. Thank you very much.
Sorry, let me just add quickly. The one thing people don't understand about small facilities, observatories such as this, is that there will be campaigns for the EHT, obviously, and there will be lots of observing collaborations and various experiments, et cetera. But there'll be a lot of time when the telescope is going to be used by researchers in single dish mode. And the value of that is enormous in terms of teaching and training. I mean, I did this for a couple of years in South Africa, trying to develop astronomy programs across the continent in various different countries. And the one thing we always came up against is no facilities in those countries. So all the students had to leave their home country, go to Europe, America, Asia, wherever, or South Africa for that matter, and then they would probably never come back. So it creates a brain drain. So for us, all of these things start adding together. If you put a facility in Tanzania, you're actually saying to the students, not only can you train here, you can remain here. And that's a big value add to the economy of Tanzania in terms of keeping those very young, bright students of all ilks. It's just, it's just really, I can't emphasize enough the importance of it. And this is true anywhere in the world. This would be, I mean, I'm doing work with some guys in Latvia. I'm doing work with some people in Latin America, and all of them are the same. You have their own facility. They now can do their own research and get their own masters and PhDs. And it's very important. And the opportunity that SHEP and the EHT is possibly giving us, I can tell you it'll be greatly appreciated. Thank you.
Very much. We passed a bit the time limit here, but there is a time break at the moment. In 7 minutes, this break will be over. So it's up to you if you want to stay here and continue the discussion, or you can shift to the main room and be back for the last part of the conference. So thank you very much for your participation and your amazing presentations.